I'm going to talk about extreme soil erosion physics, what we need to learn about supersonic rarefied gas interacting with granular materials for landing on the moon, Mars, and beyond. I'm Philip Metzger, and my co-authors are Douglas Fonts and Daka Sapkota. We're of the University of Central Florida. Now, we're not really talking about what do we need to solve in order to return to the surface of the moon. What we're talking about is using the surface of the moon as an opportunity to access physics that we cannot access here on the Earth. And this is an area of deep unsolved physics. It's a coupled flow problem that involves supersonic, that is compressible gas flow, shock waves, rarefied transitional and continuum regions in the flow, turbulence, in the transitional, and we don't know about the rarefied flow. There's been very little work on the spectrum of turbulence in transitionally and rarefied flow. It's a complex fluid because there's a granular phase, including phase change in the granular material from solid-like to liquid-like to gas-like or dispersed particulates. And the regimes of interaction between the gas and the granular are very diverse. We've already identified 5 or 6 different regimes of interaction, and the more we study this problem, the more we realize there is so much here that we don't understand, and we are hampered in our ability to access the physics. There's been a lot of research here on the Earth studying how desert winds blow sand and how it emits dust into the upper atmosphere. So the boundary layer can push sand grains along. There's turbulence, including splashes that can lift sand and push them along. But in the vacuum of the moon, you've also got the stagnation of the gas against the particles driving down into the vacuum in the pore spaces of the soil, possibly fluidizing the soil, and you can have a transition to a fluid-like flow, a rolling layer, and this is vastly more complicated than a desert sand physics problem, we've had barely any ability to study it so far. Speaking of the shock effects, this was an experiment I did a few years ago. The gravel on the surface was moved not by the erosion, but entirely by the shock splash from the igniting rocket engine. But you can see all the gravel from the surface was lifted off the surface and blown away by that shock impingement. This is an experiment that I did firing a solid rocket motor into a deep sand bed, which induced bearing capacity failure, which is one of the regimes that we see in the physics. But look at the sidewall of that crater. It's fluidized because there's no retaining force holding it up in that vertical position other than the traction of the gas moving uphill along the side. And so the sand is put into a fluidized regime, and you see waves and very complex interaction of the gas and fluid and sand. Now this we can access here on the Earth, but when you go into rarefied conditions, then we cannot do these sorts of experiments yet. Now we've done all that we can do using the available data. We've looked at the terrain under the lunar landings. We've looked at the videos and we've analyzed them in the extreme. We've done experiments in vacuum chambers, but these are limited. We can only do limited size scale experiments. And trying to blow supersonic gas into a vacuum chamber while maintaining the vacuum is very hard, especially if your chamber has to be pumped down in real time and the dust would ruin the pumps. But we can see erosion actually gets faster in rarefied conditions, and we don't understand the physics of this. We've analyzed experiments on volcanoes. We've done experiments in reduced gravity flights. We've used live rocket engines, and we've used cold gas, and we've analyzed it. And this work is still ongoing, but we really need to get data from the surface of the moon in the extreme environment. So what we need are sensors on board lunar landers. But then beyond that, we need to put sensors that are stationary on the moon near the lunar landings. And then ultimately, we should be developing a test bed on the lunar surface with the goal of making fundamental advances in the extreme flow of fluids. This should have thrusters with a propellant distribution system controllable from the Earth. There should be sensors with advanced capabilities, too large to mount on landers, and incrementally built up over time, robotics to prepare the regolith for the experiments. And this is the sort of capability that we can do science on the moon and make fundamental advances that will not only support NASA, but will support a wide variety of technology and science applications. Thank you for your attention.